All right. So, from the previous hour, we have left at this question number 4. And at this point, the question asks us this: determine the present worth of the following series of uniform annual cash flows based on an interest rate of 12% per year, compounded annually. Now, the assumed compounding and the assumed interest rate are easy actually this time. So interest rate is 12% and the compounding occurs annually in annual terms, and these are the end of the year payments. However, if you check the cash flow structure, we have $0 at time 0, 1,000, 2,000, 3,000, and 4,000 in the end of first, second, and third and fourth years. They are positive. And in fifth and sixth years, 4,000 will remain constant. So by the end of the first year, we will start from 1,000, then it's going to become 2,000, increasing $1,000 in each following year. But when it reaches to $4,000, it is going to stop increasing. And in the end of remaining years, it is just going to be $4,000 of cash flow in future years. Okay, so the cash flow diagram is like that. That is the cash flow diagram of this question. Now we are going to decompose this cash flow diagram into two parts. First, we are going to focus on the first 4 years where we have a gradient series, and in the last 2 years we have a simple uniform series. Okay, so what we are going to do is this: we are going to assume that we have a 4 years of gradient series here. Base payment is $1,000, and the annual increase in the consecutive years is $1,000 again. First of all, we have a 4 years of gradient series of $1,000 gradient, which should be converted into a uniform series by multiplying it with the gradient series factor A over G under 12% interest rate for 4 years. So this evaluation here gives us what? It gives us the uniform counterpart of the gradient series that we have. And we need to add this base amount, $1,000, which is going to be paid in 4 years after the gradient amount. And that square brackets here is going to give us what? It is going to give us a uniform series. And that uniform series is going to be multiplied with a uniform series present worth factor under 12% interest rate for 4 years. So this calculation here, the first calculation until this plus sign, is going to give us the present worth of these 4 cash flows. Now for the second part of these cash flows, we have a uniform series in the end of the 5th and the 6th year. And actually, this uniform series is a 2 years of uniform series, assuming that the 4 is times 0 and end of the 5th and 6th years are times first year and the second year. We have a 2 years of uniform series. So by multiplying this $4,000 with P over A, we are going to calculate the present worth of this uniform series at the end of the 4th year. So these 2 years of uniform series by the end of the 5th year will be discounted to the 4th year by multiplying $4,000 with a uniform series present worth factor under 12% interest rate for 2 years. However, after discounting these 2 uniform payments to the end of the 4th year, we need to multiply that value with an additional single payment present worth factor. So we are going to convert that value to present worth at time 0. So by multiplying that value with single payment preferred factor under 12% interest rate for 4 years, we will be discounting it to time 0. And at this part, we are going to calculate the present value of the second part of this decomposition. And the values are always checked from the first table. Here because we have discrete periodic compounding with discrete payments. And the final value is going to be 11,461.17 if we use the tables. Okay. Now, we're going to learn about the capitalized word method. Now, let's just say we have a project. This time, the project does not have a finite length, which means the revenues or expenses in the future are going to continue for an infinite length of the time, or a, not maybe infinite, but a very, very long time. Okay. In that case, the present word method is going to be called the capitalized word method. And we use the capitalized word method to compare alternative investment plans when the needed service of these investment plans are indefinitely long. Okay. So we are going to see an example in the question. The capitalized worth of a perpetual series of end of the period uniform payments A is easily calculated. So if you remember, if we have a uniform series of payments which are made in the end of n years, we multiply this uniform series with P over A, the uniform series present worth factor under I% interest rate for n years. And that, and when n goes to infinity, the present worth factor formulation is going to be taken to the limit as n goes to infinity. And as n goes to infinity, you can easily realize that the value of this ratio is going to be converged to 1 over I. And therefore, under capitalized word method, the present word calculation of a uniform series will be simply equal to the uniform series divided by the interest rate as decimal. Okay. So the capitalized worth of a project with interest rate I% per year is the annual equivalent of the project over its useful life divided by I. So I is going to be used as decimal, of course. Now, in this question 5, we are going to experience such a situation. It says a new bridge across the Cumberland River is being planned near a busy highway intersection in the commercial part of a Midwestern town. So we are going to construct a new bridge. If we are going to construct a new bridge, then the potential benefits of this bridge is going to occur for indefinitely long amount of time. So the initial construction cost of the bridge is $1.9 million. The initial construction cost of the bridge is $1.9 million, and the annual upkeep is estimated to be $25,000. So in the end of every year, we need to pay $25,000 for the annual upkeep. And in addition to annual upkeep, major maintenance work is anticipated every 8 years at a cost of $350,000 per occurrence. So we are just going to pay a major maintenance work in the end of every 8 years. In the end of every 8 years at $3,500,000. The town government's minimum attractive rate of return is 8% per year, compounded annually, and the bridge has an expected life of 96 years. What is the capitalized worth of this bridge over this period? So what is the present worth? Actually, capitalized worth means present worth. However, because 96 years is assumed as an indefinitely long amount of time, we are just going to use the capitalized worth approach, and we are just going to create the uniform equivalent of these payments. Then we are going to divide the uniform equivalent to the interest rate as decimal, which is 0.08, to calculate the capitalized worth. Now, how do we do that? How do we do that? So you see, we have initially a negative payment of $1.9 million to construct that bridge. Other than that, in the end of every 8 years, we need to pay $350,000 of major maintenance cost. However, we need to find the annual equivalent of these $350,000 to 8 years. So how do we do that? by using the uniform series sinking fund factor. We are going to, since we are going to pay this amount in the end of the 8 years, instead of that, we are going to multiply this value with A over F over 8 years under 8% interest rate. So we are basically trying to calculate the installment amount that we need to put aside in the end of a year in order to collect $350,000 in 8 years. So by multiplying this value with A over F, we are going to find the uniform counterpart of this $300,500. Okay. So 300,000 plus 50,000, $350,000 here. Now that is not enough. Of course, we need to calculate the present worth. We need to calculate the present worth of this uniform series, because even though we distribute the payment in the end of 8 years to 8 years installments, we are going to continue these payments for 96 years. So the uniform series that we construct here is going to continue for 96 years under 8% interest rate. So if we multiply that value with P over A, we are going to calculate the present worth of these values. Now, we are going to do the same here, but here, this upkeep cost, which is $25,000, the upkeep cost of $25,000 is directly multiplied with the uniform series present worth factor under 8% interest rate for 96 years. Now, we need to evaluate that part, and that part, so this $350,000 multiplied with the sinking fund factor is evaluated here. Now, we are not going to check P over A values or A over P values from the table, because 96 is a very, very long amount of time. And we are going to apply a capitalized worth approach here. So instead P over A, we are simply going to assume that P over A, as you can see here, is equal to 1 over I for an indefinitely long amount of time. And assuming that 96 is very long, instead of using P over A directly, we are going to use 1 over I, as you can see here in both cases. And the result is going to be minus $2.6 million approximately. Okay? So right now, if the government of this city allocates $2.6 million approximately, okay, $2.6 million approximately, then they will be able to sustain that bridge for 96 years for all maintenance costs and upkeep costs. Okay, now we can move to another analysis method, which is the future worth method. And in the future worth method, we are going to compare investment alternatives by looking at their future values in the end of the investment period or the project period. So let's just say you are given a project at time 0, there is an initial investment cost, and in the future time periods, in the end of every period, there is a positive or negative cash flow. What is the future worth or end of year end worth of this project? So this time, instead of calculating the future worth, present worth of everything, we are going to calculate the future worth of everything. We are going to discount them to the future, not today. Now, how do we do that? First of all, the initial cost of cash flow 0 is going to be multiplied with single payment compound amount factor for I% interest rate under n years. Okay. And the rest is going to be the same. So in the end of first year, the cash flow is going to be multiplied with, again, single payment compound amount factor. However, this time for n-1 years under I% interest rate, so on and so forth. The only thing that is not going to be multiplied with anything is the final amount, the final payment amount in the end of n years. So everything this time is going to be discounted to the future, not to present. So you see, for year K, if we have a cash flow at the end of period K, it is going to be multiplied with the single payment compound amount factor for n minus K remaining years, and n is the total lifetime of the project. we are going to apply a summation from 0 to n for all cash flows here. Now let's solve question 1 again, but this time we are going to evaluate the future worth of this potential improvement project, not the present worth, but the future worth of it. And again, in part A, we are going to assume a 20% minimum attractive rate of return per year, which compounds annually. And in part B, we are going to assume a minimum attractive rate of return for 20%, which compounds continuously. So again, remember from question 1, under the assumptions of part A, the investment, the project was very economically justifiable. However, under the assumptions of part B, it was not economically justifiable. So the same results should be observed in this analysis as well. Remember now, whether you implement the present worth of the future worth methodology, if alternative plans are of same years, okay, they consist of same years, then the results should be the same. So here we are going to see the same results. Let's calculate the future worth of this cash flow diagram under 20% interest rate, which compounds annually. So first of all, the initial investment of negative $25,000 must be multiplied with single payment compound amount F over P under 20% interest rate for 5 years. Plus, we have a uniform series of $8,000, as you can see, and we need to multiply this $8,000 with the uniform series compound amount factor, F over A, under 20% interest rate for 5 years. Finally, the final value of this, the second enterprise of this investment of this equipment is $5,000. Because this cash flow is going to occur in the end of year 5, we do not need to touch that. We are just going to leave it as it is. And the final result is going to be $2,325 approximately. So you see the future worth under 20% minimum attractive rate of return, which compounds annually, is positive. And again, we have an economically justifiable project here. For part B, we assume that the minimum attractive rate of return under 20% interest rate compounds continuously. And in that case, the initial cost is going to be multiplied by a single payment compound amount factor under continuous compounding. We again have square brackets here, but the interest rate and the number of years are the same. And $8,000 is going to be multiplied with uniform series compound amount factor, but again assuming continuous compounding. So all that changes, all that is changed here is that we are going to check these compound factors not from the first table where we have annual compounding, from the second table where we have continuous compounding. Okay. And that is going to bring us a negative $870.30. And you see under a minimum attractive rate of return for 20% that compounds continuously, the investment is economically unjustifiable. Now, this time we are going to apply the future worth methodology to question number 2. Remember, we have a retrofitted heat system project in question 2. So let us remember it. Question 2. So we have the initial cost of $110,000. In every year, we save $30,000 worth of energy. And in the end of the 6-year period, we will be able to sell this system from $8,000. Okay. This time we are going to perform future worth analysis. So let me go back to the question. This time we are going to apply a future worth analysis. Again, in part A, we are going to assume that we have an annual compounding and the annual savings occur at the end of years. And then we will have a continuous compounding, and the annual savings occur continuously over the year. So the first part is easy. So we are going to calculate the future worth under 15% nominal interest rate, where the compounding occurs annually, again, annual compounding. And this $30,000 saving is going to be made in the end of the first year. In that case, the initial cost, $110,000, will be multiplied with the single payment future value, future compound amount factor, FP, which is simply 1.15 to the power 6. Okay, that is 1.15 to the power 6. Plus, this $30,000 is going to be multiplied with uniform series compound amount factor under 15% interest rate for 6 years, which can be looked from the first table. And the final value of the heating system, when we want to sell it in the end of the 6th year, it is going to be $8,000. We do not multiply it with anything because our objective is to calculate the value of the system at that time point, and the result will be 16,170. Now, in the second assumption, if we assume a continuous compounding, all these equations are going to be constructed with square brackets instead of ordinary brackets. And this time, when we are calculating the future value of these $30,000, we will assume that these $30,000 savings are going to be made constant rate throughout the year, not just in the end of the year as a total lump sum. So throughout the year, from beginning to the end, we have a constant speed savings of $30,000 in total per year, and we are going to multiply that with the continuous payment, continuous compounding, uniform series compound amount factor. So we have F over A bar. We check that value from our second table where we have continuous compounding and discrete payments, and we check that value from our third table where we have continuous compounding and continuous payments. And the final result will be $29,365 here. Now, this is the same question as before. Again, we have, so this was actually question number 5, not 5, but 4. Question number 4. So we have a cash flow diagram like this. So question 8 is the same question, but this time we are being asked the future value under 12% interest rate, and it compounds annually. So again, we have the same cash flow here, but this time we are going to decompose this cash flow diagram into two parts in a different fashion. So this time we are going to assume that we have a complete gradient series for 6 years, starting from first year until the 6 years, and at every year the gradient size is going to be $1,000, and the base amount is $1,000 in the end of the first year. And as a second part of this flow diagram, we will have a negative $1,000 and negative $2,000 in the end of the 5th and the 6th years. And the future worth under 12% interest rate is going to be computed by calculating the future worth of these two decomposed parts. Now, if you calculate the net cash flow diagram by summing up these two cash flow structures, you are exactly going to get this value. So if you subtract 1,000 from 5,000, and if you subtract 2,000 from 6,000, you are exactly going to get this constant $4,000 in the end of year 5 and year 6. Now, the future worth of this cash flow diagram is going to be computed by calculating the future worth of both cash flow diagrams. So in the first one, we have a gradient series with base amount of $1,000 and a gradient amount of $1,000. The gradient is multiplied with A over G to convert the gradient into a uniform series under 6 years, for 6 years under 12% interest rate. Then when we sum this uniform counterpart of the gradient series, the summation of the base amount is going to be multiplied with the uniform series compound amount factor to calculate the future value of the first diagram. Now for the second diagram, we have a shorter gradient series for 2 years only. So this is the first year, 5 year, year 5 is the first year, and year 6 is the second year. So we have a base amount of $1,000 and a gradient of $1,000. We multiply this with A over G to convert that gradient to the uniform equivalent. Then summing it up with the base amount of $1,000, we multiply it with a 2 years of uniform series compound amount factor under 12% interest rate to compute the future value at the end of the 6th year. Now remember, we have a negative sign here, which means we are subtracting the values that we obtained here. And all of these values can be checked from the uniform series compound, the annual compounding table. So the discrete periodic compounding table. And the result is going to be 22,621. Okay, so this is going to be the last part of our lecture today, and that is going to be the annual word method. So let's just give an introduction to that, and maybe we can solve a question related to that. Then we are going to give a break. The annual word, or the equivalent uniform annual series, so we have two names for the annual word. We can call it annual words, or another terminology that is used for annual word is equivalent uniform annual series, which is abbreviated as EUAS. In Turkish translation, yıllık eşit mali eşdeğeri. Okay? Yıllık eşit mali eşdeğeri diyebiliriz. Equivalent uniform annual series. Yıllık eşit mali eşdeğeri. So we can use the annual word or equivalent uniform annual series or yıllık eşit mali eşdeğeri. Okay, in all languages we can give a expression for the annual word. So for a given series of cash flows is the equivalent value of the cash flows into a series of uniform annual payments. So this time we are not going to calculate the present word or the future word. Instead, we are going to convert everything to the uniform installments, uniform payments made in the end of every period. Okay? So how do we do that? It is easy. First, we calculate the present word. Then we multiply the present word with the capital recovery factor for n years. We can easily compute the annual word of everything. Okay? So an approach to calculate the annual word is this. First, calculate the present word. After calculating the present word, multiply the present word with the capital recovery factor for n periods under I% effective interest rate per period. Then you will be able to calculate the present word. Now, you know, the present word factor for single payment is 1 plus I to the power minus k. And finally, the uniform series capital recovery factor will be I times 1 plus I to the power n divided by 1 plus I to the power n minus 1. So let's apply this. So let's apply this technique to this question. And we are going to calculate the annual word of this cash flow diagram. So you see, we have a cash flow diagram. At time 0, we have a negative cash flow of $600. At time 1, we have 400, 300, and 500. At time 1, 2, and 3, let's just say these are the periods. In the end of the first period, we have a positive cash flow of $400. Then in the end of second period, we have a positive cash flow of $300. And in the end of period 3, we have a positive cash flow of $500. Then again, we have a negative cash flow of $600. And repeatingly, we have 3 positive cash flows. And in the end of the third period, once again, we have a negative cash flow diagram. Actually, starting from time 0, in the end of the third, 6th, and 9th periods, we have negative cash flows of minus $600. And then we have a repeating periodic behavior of these cash flows in the end of the every first, second, and third period, so on and so forth. Okay, now the question is this. Is this investment plan economically justifiable under an annual minimum attractive rate of return? So the question assumes that these are annual series. So each period here is a year, and these are end of year payments. And under a yearly minimum attractive rate of return 9%, is this investment economically justifiable? Now, you can either use the present worth method to calculate the present worth of everything, or you can use the future worth to calculate the future worth of everything. If the present or the future worth is positive, so if one is positive, the others should be also positive. In that case, you can say it is economically justifiable. However, for such a periodically repeating cash flow diagram, it is a much better idea if we just want to calculate the annual worth. Now, actually, this component, so let me draw that component to you. We have this component. So we have negative $600 here. Then we have $400, $300, and $500 here. So this 3 years component, it is repeating itself again and again and again. Okay, it is repeating itself again and again and again. So instead of focusing on the whole cash flow diagram, why shouldn't we just focus on this repeating cash flow diagram and calculate the annual worth of it? So we are just going to calculate the yearly equivalent amount of this 3 periods cash flow diagram, and it is going to be the same as for all repetitions of this cash flow diagram. So we are just going to focus on one part of it. Therefore, the annual worth method is going to be an easier approach to solve such a question. And how do we do that? First, we calculate the present worth of these 3 periods, first 3 periods, excluding 600 here. We are going to calculate the present worth of the first periods cash flows. So we have minus 600 in the beginning. 400 is going to be multiplied with single payment present worth factor under 9% for 1 year. We multiply $300 with the present worth factor for 2 years under 9% interest rate. And finally, we have $500 multiplied with the single payment present worth factor under 9% interest rate for 3 years. Now, single payment present worth factor is calculated as 1 plus the interest rate, which is 1.09 to the power minus number of years. And after calculation of all of this for 3 years, then we are going to multiply the present worth with uniform series capital recovery for 3 years under 9% interest rate to calculate the equivalent yearly payments for this present worth, which is going to be $160.22. So this means what? Under a 9% minimum attractive rate of return, instead of experiencing such a cash flow diagram, instead of that, if we are just paid $160.22 in the end of every year, that cash flow diagram is going to be the same as this one. So for 12 years, instead of getting cash flow like this, if we just get cash flows in the end of every year as $160.22 under a 9% minimum attractive rate of return, that plan or that cash flow diagram is going to be equivalent to this one. Now, for the last part, we are going to talk about the capital recovery cost. But before that, let's just give a break.